Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
Nuclear physicists have found a new way to use the Relativistic Heavy Ion Collider, RHIC, a particle collider at the U.S. Department of Energy's Brookhaven National Laboratory, to see the shape and details inside atomic nuclei. Through a series of quantum fluctuations, the particles of light, a.k.a. photons, interact with gluons, glue-like particles that hold quarks together within the protons and neutrons of nuclei. Those interactions produce an intermediate particle that quickly decays into two differently charged pions pi. By measuring the velocity and angles at which these pi plus and pi particles strike RHIC's star detector, the scientists can backtrack to get crucial information about the photon, and use that to map out the arrangement of gluons within the nucleus with higher precision than ever before. This technique is similar to the way doctors use positron emission tomography, PET scans, to see what's happening inside the brain and other body parts, said former Brookhaven Lab physicist James Daniel Brandenburg, a member of the STAR collaboration who joined the Ohio State University as an AS. But in this case, we're talking about mapping out features on the scale of femtometers, quadrillionths of a meter, the size of an individual proton. Even more amazing, the STAR physicists say, is the observation of an entirely new kind of quantum interference that makes their measurements posy. We measure two outgoing particles and clearly their charges are different. They are different particles, but we see interference patterns that indicate these particles are entangled, or in sync with one another, even though they are distinguishable particles, said Brookhaven physicist and STAR. That discovery may have applications well beyond the lofty goal of mapping out the building blocks of matter. For example, many scientists, including those awarded the 2022 Nobel Prize in Physics, are seeking to harness entanglement, a kind of awareness, and interaction of physically separated particles. One goal is to create significantly more powerful communication tools in computers than exist today. But most other observations of entanglement to date, including a recent demonstration of interference of lasers with different wavelengths, have been between photons or identical electrons. This is the first ever experimental observation of entanglement between dissimilar particles, Brandenburg said. The work is described in a paper just published in Science Advances. Shining a light on gluons. RHIC operates as a office of science user facility where physicists can study the innermost building blocks of nuclear matter, the quarks and gluons that make up protons and neutrons. They do this by smashing together the nuclei of heavy atoms such as gold traveling in opposite directions around the collider at close to the speed of light. The intensity of these collisions between nuclei, also called ions, can melt the boundaries between individual protons and neutrons so scientists can study the quarks and gluons as they existed in the very early universe, before protons and neutrons formed. A recent discovery using clouds of photons that surround RHIC's speeding ions suggests a way to use these particles of light to get a glimpse inside the nuclei. In that earlier work, we demonstrated that those photons are polarized, with their electric field radiating outward from the center of the ion. And now we use that tool, the polarized light, to effectively image the nuclei at high energy, Xu said. That in turn lets physicists look at the gluon distribution both along the direction of the photon's motion and perpendicular to it. That two-dimensional imaging turns out to be very important. All past measurements, where we didn't know the polarization direction, measured the density of gluons as an average, as a function of the distance from the center of the nucleus, Brandenburg said. That's a one-dimensional image. Those measurements all came out making the nucleus look too big when compared with what was predicted by theoretical models and measurements of the distribution of charge in the nucleus. Measuring just along the photon's direction, or not knowing what that direction is, results in a picture distorted by these photon effects. But measuring in the transverse direction avoids the photon blurring. Now we can take a picture where we can really distinguish the density of gluons at a given angle and radius, Brandenburg said. The images are so precise that we can even start to see the difference between where the protons are and where the neutrons are laid out inside these big nuclei. The new pictures match up qualitatively with the theoretical predictions using gluon distribution, as well as the measurements of elect. Details of the measurements to understand how the physicists make these 2D measurements. Let's step back to the particle generated by the photon-gluon interaction. It's called a rho, and it decays very quickly, in less than 4 septillion ths of a second, into the pi plus and pi. To extract just the gluon distribution, the scientists measure the angle between the path of either the pi plus or pi and the rho's trajectory. The closer that angle is to 90 degrees, the less blurring you get from the photon probe. Keep in mind that all the particles we are talking about exist not just as physical objects but also as waves. Like ripples on the surface of a pond radiating outward when they strike a rock, the mathematical wave functions that describe the crests and troughs of particle waves can interfere to reinforce or cancel one another out. The interference is between two wave functions of the identical particles, but without the entanglement between the two dissimilar particles, the pi plus and pi. This interference would not materialize, said Wangmei Zhao, a star collaborator at the University of Science and Technology of China, Henan. This is the weirdness of quantum mechanics. Could the rho's simply be entangled? The scientists say no. If the pi plus and pi were not entangled, the two pi plus, or pi, wave functions would have a random phase, without any detectable interference effect, said Kai Yang, a star collaborator from Shandong University in China, who also helped lead the analysis for this result. The STAR team used computational resources at the RHIC and Atlas Computing Facility, Scientific Data and Computing Center at the Brookhaven Lab, the National Energy Research Scientific Computing Center, NERSC, a DOE Office of Science User Facility at Lawrence Berkeley National Laboratory, and the Open STAR collaboration. Tomography of ultrarelativistic nuclei with polarized photon-gluon collisions. Science Advances, 2023 doi. 10. 1126, Sci-Adv. ABQ 3903 DOE, Brookhaven National Laboratory. New type of entanglement lets scientists see inside nuclei. Science Daily, the 4th of January 2023. ift.tt/1zrljvb. DOE, Brookhaven National Laboratory. 2023, January 4th. New type of entanglement lets scientists see inside nuclei. Science Daily. Retrieved January 4, 2023 from ift.tt/1zrljvb DOE, Brookhaven National Laboratory. New type of entanglement lets scientists see inside nuclei. Science Daily. ift.tt/1zrljvb. Accessed January 4, 2023. Thanks for watching. Please subscribe my channel for more videos.